All right, so as said, this talk will be about C++ debugging LLDB and how we can make it better with Clang modules. Not C++ modules, Clang modules. So first, most of this talk will be focused on expression evaluation. So I want to start with an example of what expression evaluation actually is. So what you can see on the slide is a very straightforward C++ program. It just declares two integers, a and b, and it returns the sum of a and b as its exit code. And what you can also see is that in this case, we see the program because LLDB is currently running it, and stop the program at the last line. Line number 4, where we return the exit code. So the program is stopped, and LLDB allows us now to run comments to debug the program. So one of these comments is print, or just shortened to p, which essentially triggers expression evaluation. So let's try this out. We can run, for example, p a plus b. So a plus b is how we calculate the exit code. So in this case, we could use the print comment to find out what the exit code will be once the program actually terminated. So what the print comment is actually doing is it takes a piece of code in form of a string, and it interprets the code as an expression that will be evaluated as if it was evaluated inside the program in the current state. So what we did here is we just summed up two integers, and we got the result back. This is one way how you can inspect your program using expression evaluation. You can also change the program using expression evaluation. To do this, we can, for example, say a equals 3. So we have an expression with a side effect, which is that we assign the value 3 to the variable a. And we get something back again, mostly because assignments also are expressions in C++, and they return, or like they evaluate to the new value of the variable a. So that's not so interesting. But what's interesting is if we now run again a plus b, we get the number 13, because the value of a has changed from 2 to 3, and 3 plus 10, which is b, is 13. And this is how you can use expression evaluation to change the state of the program you're debugging. So expression evaluation is a great concept. You can debug the program, but you don't actually need to learn like a debugger-specific language. You can just use the language that you've written your original program in. So that's great. But in practice, it doesn't always go smoothly, as in this example. So let's look at a C++ program where it doesn't go smoothly. So we have again a similar setup as in the slide before. We have a vector with 3 integers in it, vector v, which is a local variable, and then we return the last element of the vector as the exit code. Again, we stop the program LLDB, and now we use expression evaluation to inspect or change the program. So let's say we are interested in the first value in our vector. So what we do is we evaluate the function that would return, or an expression that would return the first element. So we would evaluate v.front, and what we get is instead of the value, we get an error about some symbol that seems to be related to the front method missing. And because of this, LLDB is not able to evaluate our expression. All right, it's not clear what's going on, but apparently we're unable to inspect the vector this way. So let's try another way. Let's try to go over the iterator. So let's call begin and see if we can go over the iterator to the first element. Now we get another error about some incomplete return type from begin. And this again looks incorrect, and we can't inspect our program state. So just using expression evaluation, we're more or less stuck now when we want to find out what the first element is. There are some workarounds in LLDBs, but just using expression evaluation, that's how far we could get in this example. Let's try actually changing the program state just to see how bad it can get. So we call in place back on the vector, and LLDB actually claims, even though this is C++ 11, that vector has no in place back method actually. And it will just error out and say there's no such method, and we get no result back. So we also can change the program state. And this talk will be about why this is happening and how we can fix it with Clang modules. So let's go under the hood of LLDB and see how expression evaluation actually works. So expression evaluation LLDB takes, for now, 2 components that we're interested in. One is the expression evaluator, which is just like an abstract concept where we just say we put all the general expression evaluation logic in it. And then we have Clang. And with Clang, I mean Clang as a library, not like the Clang binary we have on disk. It's like the Clang parser, Clang codegen, the things you know from the Clang repository. And the fact that we actually use Clang in LLDB, or well, first I should say, so this Clang is actually what we use to parse your expression. And the fact that we use actually a compiler to parse your expression and not like some hand-rolled expression parser that you wrote from scratch makes LLDB actually pretty unique. Other compilers may use a handwritten expression parser, and that has different advantages and different disadvantages, obviously. But we will get, over the course of this talk, into what are the advantages of actually having a full compiler here. So let's try evaluating the expression to see how this actually works. So we have an expression 1 + 2, and we get this from someone, either a user calling the print command, or, for example, some script that uses the LLDB scripting API to ask LLDB to evaluate this expression for it. But we get the code as a string, and then we wrap it in a function, which is just some small thing we actually do, because we can't have freestanding expression in C++. But otherwise, we just take the code and we put it to Clang. And then the Clang parser starts working on the code, and it produces an AST for us. And we can type check the AST, and then we can code gen the AST, all with Clang. And what we get back from code gen is LVMIR. And then the LVMIR goes back to the expression evaluator, and now we run the LVMIR in some form. There are some ways how this can happen. One is, for example, we interpret the IR, like locally in LLDB, or we compile it and we inject it into the target process and run it there. But in some form or another, we get a value back, and we display it to the user. So 1 + 2 = 3 in this case. All right, let's take a more complicated expression, because usually debuggers are not used to calculate 1 + 2. So let's calculate what is A + B. Well, the first question we have to ask ourselves, what is A and what is B? Is it A + B from the introduction example? We don't know, and Clang doesn't know. Like, there's no inherent knowledge what A and B is. So we need context, and the context in LLDB is provided by something called the target. The target is LLDB's concept that essentially contains a debug information, which is emitted when you compile your program, and also the current state of the running process, like because LLDB either started your program or it's attached to a running program. So what happens now is that Clang is parsing the expression A + B, and during the parsing process, it encounters things it doesn't know about. And Clang has an API where it can ask about things it doesn't know about, and LLDB implements this API to essentially provide information back to Clang so that it can actually understand the expression it's currently parsing. So let's make an example. We start parsing, and we get first the question, what is A? Because it's the first part of the expression. And if we look at the target, and I put the source code below the target, we see that A is a variable foo, is a variable of type foo, and foo is some class. So let's first take class as like an AST node and put it into the Clang AST we're currently building. And then let's just say, well, the variable A is just a variable of this type. The same goes with B. I know this is not a parsing order, but for simplification. So next is B, and it's also a variable of type foo. So we do the same thing again. And then we have plus. What is plus? Is it integer addition? Well, foo has an operator plus, so we know it's actually a call to that operator. Now we have a full AST in our expression evaluator. We can again run LLVMIR, and then in some form or another, we get a result back. All right, so let's make one more example where it fails. So we have an expression, v.size. Again, we don't know what is v and what is size, so we need context. And the context provided by the target, and the target program is just doing two things. One is we include a vector from the standard library, and one is we instantiate a vector with integers. So we have a vector of integers v. So what happens now is we start parsing with Clang, and Clang will ask us, what is v? Well, we know from debug information that there's a vector of int in your program, and we know that v is of type of this vector, type of vector of ints. And then we have a size call, and the size call is a call to the member method of vector of int, and it just returns the size. And what happens now is we get LVMIR back, and we evaluate it. But this time we don't get a result, we get an error. And the error is there's no vector size in the target. Okay, so why do we get this error? Well, to understand why we get this error, let's take and look what the target actually is. So LLDB knows certain things about the program, and those things usually come from debug information. This is mostly like types. There's also a runnable state, but just like things like types come all from debug information, or mostly from debug information. In this case, we only talk about dwarf, so not like other formats. So dwarf describes a few things that LLDB can read and use to understand what your program is essentially built, how your program is essentially built. So dwarf describes, for example, the functions you used in your program and their signatures. So for example, it knows the the parameters and the return value and the name of the functions you have in your program. It knows classes, what members they have, their inheritance, and it knows template instantiation. So it knows that the program has a vector of int. But there are a few things that Dwarf doesn't describe. One thing is function body AST. So if you have a function, Dwarf describes that there is a function, but it doesn't describe the AST, which is essentially the function body. This has some implications, and the biggest one is that if LDB wants to call a function from the expression evaluator, it needs to have the function in a compiled form in the target. So in the previous example, we tried to call size. And because size is a function, we don't have the body, we need to have the size function compiled in the target. But our target never used the size function, or like, for example, it got inline or any other reason. But for some reason or another, our target has, in this case, no size function that we could call. So we can't do anything else. Like if there's no callable function, the only thing LDB can do is error out. We can't evaluate function calls if we don't have a callable function in the target. Something similar is happening with templates. So Dwarf doesn't describe templates, which means if you do any kind of metaprogramming in the LLDB expression evaluator, you can only use templates with template arguments that are exactly like that used in the compiled program. If you use any other kind of template argument, we can't do anything. We have no templates, and we can't do any kind of metaprogramming otherwise. So those are some severe restrictions. And it kind of sounds like shortcomings of Dwarf, but some of the things are just not something that Dwarf was designed to do. Like Dwarf was not designed to be like a full transcription of the source code, so we can't just put the function body ASTs in it. So this brings up to the question, how can we fix this? And the best way to fix this is to have more information about the program that fills the holes we have, because those are the holes that essentially Dwarf has about the program. Like, for example, we don't know about your templates. And our answer for this is Clang Modules, which you probably can guess from the title. OK, so what are Clang Modules? So this is just one slide where we just leave LDB and just look what Clang Modules are real quick. So Clang Modules are Clang's precursor to the C++ modules that were mentioned in the introduction. So there are C++ modules and there are Clang modules, and they're not the same thing. Clang modules have, however, similar motivations as C++ modules. They essentially force developers to have better organized code, and also they essentially get rid of the textual inclusion of headers. Instead, we import modules under the hood. The whole way Clang modules work is essentially we take a header, we compile it, we take a header, we parse it, we get an AST out, and then we take this AST, like Clang's internal AST of your program, and we serialize it in a file. And then any future invocation of Clang or any future Clang instance that somehow uses the header can instead just go to the serialized file and load the program parts from the file as it needs it. So Clang modules have some benefits that make them a good source of program information. One is they're obviously fast because that's what they were assigned to do. They contain a lot of information that we're actually missing. So usually you'd put header files in your Clang modules. And header files contain often things like inline functions, which are like one of the reasons, like inline functions are one of the reasons why a function may be missing from your target. Or for example, templates are often in headers. So they're a good source of program information that pretty well covers the things you're usually missing from debug information. So the idea is, well, we take those Clang modules and we integrate them into LDB as another information source about the program. So how do we go about this? Well, there are 3 steps. One step is we need to find out what modules were used when you compiled your program, because those are the modules we actually need to import into LDB to get program information. Then we actually need to import the modules we found, and then we need to integrate the modules we imported into the expression evaluator. So the first step is finding the modules that were used by your program. This is relatively straightforward, because if you use Clang modules to compile your program, Dwarf is capable of expressing what modules are used when you compile your program. There are some details how exactly you need to compile your program, but usually what we have in Dwarf is a list of modules, and we can just read the list. So this is pretty easy. The second step is more complicated. There are certain module files that were used or were created when you compiled your program. But we can't just use those module files on your disk. And the main reason for this is that the Clang module format is not stable. Modifiers are supposed to be written and read by exactly the same Clang version. And as LDB is using its own internal Clang version, which may or may not be exactly the same version used to compile your program, we can't guarantee that we have a matching Clang to read the modifiers used during compilation. So what we do is we compile our own set of module files. Meaning if you have a module A that you use during compilation, LDB compiles its own module A when it needs it. Doing our own set of modules fixes the problem of working around the fact that the Clang module format is not stable. But it brings up another problem, which is if we build our own set of modules, the type information in them needs to be ABI compatible with the target. So for example, you have a struct in your header, and you compile your program, and one of the members in your struct is like if-def with some define. Is if-def with some define. We need to have this define set in exactly the same way when we build our own module as when you compiled your program. If not, we have two structs with different ABIs, and we code gen in our expression evaluator code that is ABI compatible with the target where we actually run the code. And this will lead to crazy errors. So we don't want to do this. The question is, how do we find out how exactly we need to compile the source code? And this can be a bit tricky because there are a lot of different ways how we can actually change the ABI of a program. Like, for example, it's not just defines, but it also maybe like language modes and whatnot. So this is a bit of a tricky problem. But let's just assume we have a set of modules that we can actually use and import them into LDB. So what we need to do next is we need to get these modules into the expression evaluator. The simplest way, or like the simplest approach we can take is obviously we just that LDB, when we get a question from Clang, we just look into the module file and look for program information there. But we not only need to do this, but we also still need to use the debug information. And the reason is that neither the debug information nor Clang modules know everything about your program. Like the Clang modules usually know the contents of your header pretty well. And debug information may not know things like templates, but it knows, for example, all the what is essentially what kind of declarations are in your source files. So this leads to the situation that we have two information sources, but both don't have full knowledge of your program, but combined together, they have a relatively complete view of how your program is structured. So what we need to do is we need to take these two information sources, Clang modules and the debug information, and we need to merge them essentially into one consistent AST that we can actually use in the expression evaluator to generate code and run in your target. So there are two tricks we use to merge these two information sources. And this is just like, I just give a quick overview here how this works. So this is not like a detailed explanation. The first trick is we use a prioritized lookup in LDB. Let's make an example. So we have a header file, apps.h, and it just has a single function which is inline, and it just calculates the absolute value. And then we have a CPP file. It includes the header, and it calls the inline function. All right. So let's change the view to how LDB would see this setup. LDB would see a Clang module, which we would say the header gets compiled to a Clang module. And the Clang module contains the inline function with its function body. And it also sees the target, and the target has debug information for the inline function too, but it doesn't have the function body because that can be described by dwarf, but it also doesn't have the function in a callable format because we just say the compiler actually inlined this function. So now if we want to try to parse an expression like a function call to this inline function, we have to make a choice. Do we take the function from the Clang module, or do we take the one from the target? And as a general rule, prioritized lookup works that we say, well, the Clang module just has the higher priority. So in this way, in this case, we would just take over the apps function from the Clang module. Of course, if the Clang module wouldn't contain the inline function, we would just fall back and take the function from the target, which may or may not can be evaluated because we get a function signature and we need to call the target. But the Clang module provides us a function and a function body which we can chit, and we can inject it alongside our expression into the target, and we guarantee that we have a function body we can actually call because we compile it ourselves alongside the expression. So this is the first trick. The second trick is we give template instantiations some special treatment, essentially. So again, another example, we have a vector.h, and it just declares a template, a vector of t. And I just gave it like one size method, but let's just imagine there's more there. So there's a size method in our vector of t, and that's our header. Our source file includes the header, so we have a vector of t there. It declares its own struct foo, and then it declares a vector of foo v as a local variable. So let's again switch to the way LDB sees this. So LDB sees a Clang module, and the Clang module has a vector of t, and it has the size method of vector of t, and the function body of the size method. And then we have the target, and the target has our variable v, that is our local variable. It has this vector of foo, and the vector of foo has like a function signature for size and whatnot, but I just omitted this, and I just marked this thing as red. And I will explain why in a second. And then we have the struct foo, which is just a struct we declared. All right, so let's try parsing expression from the start, v.size. First of all, we would need to resolve what is v. So v is a variable v, which is of type vector foo, which is of struct, which references foo because it's vector of foo. So what usually would happen, we would copy over v, and we would copy over all the other nodes because they all reference each other. And this has a problem that it will bring over the vector of foo. But as soon as we bring over the vector of foo in our Clang AST, we have the problem that we get, for example, the size signature, which in turn causes our Clang instance to emit a call into the target's compiled function for size, which doesn't exist because we don't call size in our program. So we want to avoid getting vector of foo in our expression AST. So what we do is we say, well, we need v, so let's just start copying the nodes from leaf to the root, which is v. So first, the leaf, struct foo. This is fine. It's not in the Clang module. We have no other choice here. The next one is vector of foo. And what we do here is we say, we don't want to copy it for the reason I just stated, but maybe there's another way to get a vector of foo. And what we do is we say, well, vector of foo is, first of all, it's coming from vector. And we have a vector in our Clang module. So what we do is we copy over from the Clang module the vector of t, and including the size function for vector of t. And now we say, well, we still need to copy over vector of foo, but this time we have both vector and we have foo already in the expression AST. So instead of copying over the vector of foo we try to avoid, we instead just instantiate the vector of t template with the vector of foo, because we have all the template arguments already in the expression AST. And the good thing is, because we use vector of foo that we generated from our template, we actually have now a size function that has, again, a function body. And we can check the function body, and we can guarantee that a function body actually exists when we evaluate the expression. And now we still have to essentially copy our vector of foo and variable v. But what we just do is we copy a variable of v and say, well, variable of v is now of the type vector of foo, but the new type of variable v is the vector of foo we just created and kind of like slipped in place by copying over the AST nodes. There are obviously some corner cases to this setup, like what happens with like template specializations. But this is just like a simplified overview how it works. Yeah. So what's the current status of the project here, or like of using Clang modules in LDB? So we split up the whole feature into parts. One is just using the C++ module in LDB, and this is mostly done for several reasons. One is libc++, which provides a standard library, is quite painful to use in LDB. There are a lot of templates which, as we said, most likely won't work in the expression evaluator. It's widely used because it's a standard library. But on the other hand, it's also easy to integrate. The libc++ has a stable API, so the whole building of our own module is much more simplified. And the state of using just the libc++ module in LDB, we're quite far. We're still work in progress, but we're mostly functional. We actually have a demo afterwards, a really short one. The second part is obviously expanding this whole thing to use all Clang modules you have in your project. Like if you're debugging LLVM, we would load all the LLVM modules for type information. But that's the long-term goal we have in mind. The main challenge here is that as soon as we load user-facing modules and we build our own set of them, essentially guaranteeing that we have the same API is rather complicated. There's a lot of ways how the API can change. And if you make a mistake, the expression evaluator will just evaluate wrong, essentially return you wrong results, which we want to avoid. All right, and with this, let's make a really quick demo. So the demo will be, if it works, the demo will be debugging a very simple program. And what the program is doing is, essentially it has a vector, and it wants to make really sure that in this vector the number 40 is in it. So the vector is like a vector of ints, and we just like triple check that the number 40 is in this vector, and this is how we well, essentially run the program here. Like the program is just doing one thing, which is checking that the number 40 is in the vector. All right. So the program starts with an assert whether the vector v, which is the only vector in our program, is sorted. And if we try to step over it, we trigger the assert. So obviously the program is buggy. So currently we are in the old LLDB without C++ modules. So let's try inspect the vector. Well, we can call on our vector, vector front, and this won't work. We call vector back, and this doesn't work. So the expression evaluation interaction with the vector is really limited. Just out of interest, let's actually try to see what happens if we actually try to evaluate the whole expression the assert is failing with, which should return false, but actually we get an error message that says that is sorted is not a member of namespace standard. So we're essentially stuck here. So let's stop using the old LDB, and let's use our prototype. So this is LDB. It's running on the same executable, and now we use modules to actually debug our program. So first of all, let's call front, and let's call back. Thank you. This is not the demo. Okay, so this is kind of boring. Like, you know, we have a whole presentation about calling front and back the vector, which is obviously, you know, low bar we have to hit here. So let's do something cool. Let's actually try to fix the whole program, because we really have the technology now. So first of all, let's call this thing here. So this is not sorted, actually. So this is why the thing is falling. So I would propose, let's just fix the program and let's sort this thing. Oh no, it's sorted. Let's step over assert. So there's some more things we do, and now we have a second assert. Okay, so the assert is checking two bools. One is double check and one is contains. So contains is true, and what contains is just binary searches. That's why we had to sort the vector. The second thing is we double check if the number 40 is really in our vector. And obviously there's a typo here. If you look at the line, it actually looks for the number 39 here and not 40. So let's fix this. Oops, actually I need to actually fix the typo here and not just copy paste. So, all right, so now we can step over this assert. Now we have a triple check, and this is the last check. And I know I'm on a timer. So this is false. And what we do here is have this really long expression, which is counting if the number 40, well, 39 in this typo again, is in our vector. So we should run this again. We should run count if with a new lambda that actually checks for the number 40. So let's do this. Oop. Oh, I need to fix the typo actually, and not just copy paste. All right, sorry. Okay, now it's true. And if everything worked right, this program should be successful. It is. And with that, I guess there are questions.
Thank you, Raphael. We
Thanks.
have time for just one or two questions.
No.
Why not?
Actually, we can. But I have to go back to the demo. Actually, I have to restart the demo. No, I can print a vector. But the problem is actually in this demo, this is why it's not fully working, is we actually have to simplify the types we print with LDB. Because if LDB actually sees the full template we get from the C++ module, the current code can't handle this. So this is why all the expressions we actually run here return simple values like int or bool or for these kind of things. But you can still evaluate just by doing like frame var or something like this. So this works fine. But you can't do it with expression, because that actually loads the whole C++ module. Maybe we can. So first of all, frame var. So this works fine. This is on video. It's embarrassing if it doesn't work. Oh, geez, the vector is empty, apparently. So this is still work in progress, the rendering. This is why it's not in production yet. Sorry?
So if we just wanted to see what was in the vector, so you could, like, there were pretty painters in the debuggers for like long time, so we could probably just use them.
Yeah, that's what.
Oh yeah, that's what I did with frame var, if I understood the question correctly.
Yes, so I was not sure what exactly problem you were solving with this. So if I was saying that if you just wanted to look at what's in the vector, you could just use pretty printer, so yeah.
I'm not sure if I understand the question. Why I can't just use frame var? Or what's the question?
Like,
it's an example here. Like obviously, if frame var works because we have like some special handling how we print a vector for you. But if you have any other data type, like you can't just do frame var and you get something reasonable out. Like you would get like whatever begin or end pointer for the vector implementation or something like this. If I understand the question correctly.
Probably I can take it offline. So
yeah, sure.
I'm looking for a 1 second question with 0 seconds for answer. Who's that?
Yeah, so if I understood you correctly, you're actually compiling the header file. So when you're saying you use modules, it doesn't mean that when you compiled your program originally, that you had to use a module then. You could just use a header file, and you would still compile it now into a module tool?
Yeah, in theory, this could work. Like you can compile your thing, like your program normally. There are some problems with. First of all, you still need to specify a way how you actually, like what modules you were actually using in your program. So if you don't use modules to compile it, to compile your program, then there's no module list in the debug information. So you would need like some alternative where you like write your own list of modules in the configuration somewhere. But sorry. Yeah, so the problem is like we don't really know if we can actually parse those header files. Are they standalone parsable or not? That's the big question. Also, there's some other technical problems. Like we can't just parse stuff. That will be very slow for like expression evaluation. Also, there's the question like if you have a header file and it's not in a module, and we don't want to parse it, like how would we approach it? Would we like try to create a module for you and then like try to compile the thing into a module for you? Like it could work. Like I don't say it's impossible, but it would really complicate the setup we currently use here.
Okay, let's thank the speaker again.